Quantum communication has long been described as the future of ultra-secure information exchange, but one of the biggest challenges has always been reliability outside carefully controlled laboratory conditions. Now, scientists have demonstrated a major breakthrough that brings this futuristic technology much closer to practical reality. In a recent experiment, researchers successfully transmitted quantum encrypted keys across more than 120 kilometers of standard optical fiber, while maintaining remarkable stability for over 6 continuous hours without requiring manual recalibration. The achievement represents one of the clearest demonstrations yet that quantum-secure communication networks may eventually operate reliably in real-world environments, forming the backbone of a future quantum internet. At the center of this breakthrough is a technology known as quantum key distribution, or QKD. Unlike conventional encryption systems, which rely on mathematical complexity to keep information secure, QKD uses the laws of quantum mechanics themselves. In classical cryptography, sufficiently advanced computers or future quantum computers could eventually crack even highly sophisticated encryption algorithms. Quantum key distribution works differently. The encryption keys are carried by individual quantum particles of light called photons, and any attempt to intercept or measure those photons immediately disturbs their quantum state. This means that eavesdropping is not just difficult, it becomes fundamentally detectable by the laws of physics. To make such systems practical, researchers need reliable sources capable of generating single photons with extremely high precision. In this experiment, the team used semiconductor quantum dots, tiny engineered structures that behave almost like artificial atoms. These quantum dots can emit individual photons on demand with exceptional purity and consistency. Because the photons are generated one at a time, they are ideally suited for secure quantum communication, where maintaining precise quantum information is absolutely critical. The particular quantum dots used in the study operated in the telecom wavelength range already optimized for modern fiber optic infrastructure, making the technology especially promising for integration into existing communication networks. The researchers combined these quantum dot photon sources with a sophisticated encoding method known as time-bin encoding. Instead of storing information in the polarization of light, the system encodes information in the exact arrival times of photons. In practice, this means that a photon arriving slightly earlier or slightly later represents different quantum states. This approach offers a major advantage for long-distance communication because time-bin encoding is naturally resistant to many environmental disturbances that plague traditional fiber optic systems. Vibrations, temperature fluctuations, and external interference can easily alter photon polarization during transmission, but timing information remains significantly more stable over long distances. In the experiment, the team engineered a highly controlled system capable of generating multiple quantum states both deterministically and randomly. Polarized single photons emitted by the semiconductor quantum dots were converted into carefully encoded time-bin qubits using a self-stabilizing optical setup. On the receiving side, an actively stabilized interferometer decoded the incoming quantum information while continuously correcting for phase drift and environmental fluctuations. This level of stabilization allowed the entire system to operate continuously for more than 6 hours without human intervention, something that has historically been extremely difficult in quantum communication experiments. Perhaps most impressive was the performance achieved after the photons traveled through more than 120 kilometers of optical fiber. Even over this enormous distance, the system maintained quantum bit error rates below approximately 11%, low enough to preserve secure communication. Under realistic operating conditions, the setup achieved secure key generation rates around 15 bits per second. While this may sound modest compared to classical internet speeds, it is already sufficient for highly secure encrypted text communication and represents one of the highest secure key rates yet demonstrated for a time-bin quantum key distribution system based on semiconductor quantum dots. The importance of this achievement goes far beyond the specific numbers. One of the greatest obstacles facing quantum networks has been stability. Many earlier quantum communication systems required constant active recalibration because small environmental changes could disrupt the fragile quantum signals. The new experiment demonstrates that time-bit encoding combined with quantum dot single photon sources can create a far more robust platform capable of operating under realistic conditions. This stability is essential if quantum encryption is ever to move beyond laboratory demonstrations and become part of real communication infrastructure connecting cities, institutions, and eventually entire global networks. The work also highlights the growing maturity of solid-state quantum technologies. Semiconductor quantum dots offer major advantages because they can potentially be integrated into scalable photonic devices using techniques already common in semiconductor manufacturing. Rather than relying on bulky laboratory equipment, future quantum communication hardware could eventually become compact, efficient, and deployable at large scale. The ability to combine these sources with existing fiber optic networks further increases their practical value. Looking ahead, the implications are enormous. As quantum computers continue to advance, concerns about the vulnerability of classical encryption methods are growing rapidly. A fully developed quantum internet would provide communication channels secured not by computational difficulty, but by the fundamental structure of quantum physics itself. Systems, like the one demonstrated here, represent early building blocks of that future. Researchers are now working toward even longer transmission distances, higher key generation rates, and the development of quantum repeaters that could extend secure communication across continental and eventually global scales. Perhaps most importantly, this experiment demonstrates that quantum communication is steadily transitioning from theoretical possibility to engineering reality. For decades, quantum cryptography was viewed primarily as a beautiful scientific idea constrained by fragile laboratory conditions. Now, with stable operation over more than 120 kilometers of optical fiber using advanced solid-state photon sources, scientists are showing that truly secure quantum communication networks may soon become technologically